number of conductors, right? These are again for machine design. When they want to design a machine with a higher torque and those kind of things. The other things is I didn't talk about it is a B, right? I talked about these two. Sorry, these two. I say either increase your current or increase your number of turns to get a higher torque, or you can have a magnets. This is the difference between the permanent magnet machine and regular induction machine. As you can hear, we call it permanent magnet machine. One of the field is a magnets. All these electric cars, Tesla, Nissan Leaf, Chevy Volt, Toyota Prius, all of them. I think Tesla is using induction machine, but they're switching to those one also. They're switching to permanent magnet machine. All of them they are using permanent magnet material for one of the fields. See, I said we need two fields, right? For one of the fields they're using permanent magnet. The reason is because permanent good material, which coming mostly from China. 90% of the material is coming from China for permanent magnet. They are a single source of permanent magnet in the whole world and controlling the price. This is something political now. Lots of people they want to come up with something, because they can control the market, You can put a magnets, very good magnets, they are very small. Think about size. They're going to put it inside the electric car. It's moving around, right? You can put it inside the car, so it should be small, and it has a huge beat, very big beat. Right? When you see a car like Tesla has a very, very powerful, startup because it has a very good motor. That's the reason. When you see the Prius has a, I'm not sure how many of you design when they drive the Prius, but it's kind of a still very good car. Very, very good car. You should look at the money you pay and what you're getting back. When you're going to drive your car, you should look at how much money you pay. Yeah, Tesla, you're paying 120K. You know that. You're paying 120K, yes, you're going to be happy with it. If you don't get you get the same performance as the Prius, you're going to go bankrupt in the next day, right? But Prius is one of the best cars. The MPG average they're getting about 50 miles per gallon. Think about it, how good is that number? 50 miles per gallon. But if you look at the Prius, you can see it's a little bit slower when it's speeding and very accelerating. If you look at Tesla, it's very fast because of motor design. The motor they have inside the machine is different. So these are the basic rules for the electrical and motor. Now I'm going to go start this one. Now this is all linear. We talked about it, right? But electric machines, they are not linear. They are rotating, right? They are rotating. Let's look at the electric machine. So, remember I draw the circuit of the DC machine here the other day? Just I'm going to draw that one again, I'm not going to draw the full stator, but look at here. Let's say this is pole N, right? We have a cylindrical machine. Inside that machine is going to something. Let me watch it. This is they call it U or they call it stator. This part is not moving. And either this material is a permanent magnet or you have a winding it's going to generate a magnet like this, right? Because if you look at here, the flux is this way, right? Flux or B is this way. So means here is the North Pole and here is the South Pole, right? So we call it the excitation system, or it could be a permanent magnet. We are building a magnet here inside the machine, right? And we talked about it. This flux is going to go this way, going this way, and half is going to come this way. This is the circuit for electric, for DC machine. I draw it on the board. It was problem 6, I think, of your homework. Not homework, your book. I draw the circuit and other thing in another class. Now, I have this rule. This is my rule, right? And I'm putting this winding. I'm going to go with a one-turn winding, to be easy, Let's say I have this. right? This one I'm putting here, what is this? This one I'm putting here. Let's look at it from this side. So this is the rotor, just let's understand what I'm putting on the board. Is a conductor like this, sitting in a slot here. There's a slot here. See? There's a slot here. Sitting in a slot here, going from here, coming this way, and coming back this way, and there is a mechanism to get this one out. So look at it, there's one conductor here, right? One conductor here, one conductor here. This is a one turn. Think about it, it's something like this, right? So now we want to generate calculate either force or voltage. Let's go with the generator. Let's go with the generator to calculate the voltage. How much is the voltage here, right? When I'm saying generator, means this one is rotating. Which way? Let's do which way? Let's say put it this way. If it's a generator, the direction of rotation is clear, right? Because somebody is rotating this machine for us, right? Now, look at this. This rotor is rotating like this, right? When I am here, think about it. There is a conductor like this, right? It's coming from here to here, right? This one, I had a cross section of this machine here, right? So the B or phi is this way, right? So we want to find out the voltage here. I'm gonna put another picture of this one here. Let's put it this way. So this one is this conductor coming down. And this is the wire coming from here, wire coming from here, right? And this conductor is rotating this way. B is like this. This is the N, sorry, this is a B. And this one is rotating like this, right? This conductor is attached to this rotor, right? This rotor is moving this way, right? Now I want to calculate the induced voltage in this conductor. So let's look at here. How much voltage is induced in this conductor, in this position? Can somebody tell me? What is it? Exactly. See, if you look at this conductor, the omega m is this way, but the linear speed is this way, right? Tangential to here, right? And B is this way, right? What's the angle between D and B? 180 degree, right? So cosine of that is 0. How about here? This one is moving this way, right? And B is going this way. What's the angle between this one and the B? 0. Keep in mind. 180, 0. A little bit different, no? So, but still cosine of 0 is how much? No voltage generation, right? No voltage generation. Let's say this is the position 1. I call this one position 1. So I'm going to plot the B. I'm going to plot the voltage here. And let me see which way is going to get polarity. Polarity is going to change, but I'm going to plot the voltage for this top conductor. This is the top conductor, right? If I'm going to find the polarity, I'm going to use my right hand. We say B is here, so B is here, B, we are moving that way. Let's draw it for this one is easier. So we said B is coming this way, right? B coming to my hand. Now, how I put this one in the direction of B? B. Huh? Here is this one is going here, this is position 1. So this is in position 1, this is the position 2. So now is a kind of, yes. Look at here, B is coming to my hand, this one is moving off, right? So the voltage is going to be where? The quantity of voltage is going to be inside the board. So basically E is going to be this conductor. Let's say it's here E and E, right? See, this is inside the board. This is outside the board, right? Look at this conductor here. Here it's difficult to show it because the angle is 0. It's very difficult to show it in the hand. But here, if you look at it, B coming through my hand, right? So this one, what's the speed here? Up, right? It's rotating this way, right? But the linear speed is tangential to this point, right? V is like this, right? So V, E is going to be like this, right? The positive is going to be here, right? Now, what is going to change? I'll show you what is going to change. Now, how much is the voltage here if I am in position? In position 1, we say 0, right? This is the position 1. In position 2, how about position 2? Is maximum. Why?
Because it's 90 degrees.
Yeah, because the angle between the B and V is a 90 degree. How about here? Look at here. When he was here, V is like this, right? Tangential to this circle, right? B is here, right? This is the angle, right? So basically, here is 0. Here is going to change gradually to get to 90, right? So basically, here is maximum. If you look at this one, in position 2, it's going to be maximum, right? In position 1 is 0. In position 2 is going to be maximum, right? Let me finish this one. So when I go to, forget it, so we are looking at only this conductor. I'm going to go to position 3. This conductor was in position 1, went to the position 2, now it's going to position 3. How much is the voltage again?
0.
Again 0. This is the position 3. Now we are going to go to position 4. How much is the voltage?
Negative max.
Negative. Going to go back to position 1. Again to 1. So this is the voltage induced in this conductor. Right?
The voltage polarity you refer to here, which position you refer to?
Huh?
Which position you refer to?
This one is this one, the lower conductor. And if you look at this conductor here, here is negative, here is positive. I put negative here and positive there. But if you keep the polarity this way, see, when you are going from here to here, the voltage is positive, right? But when you go from here to here, your voltage is negative. The polarity changed, right? You can see that, right? So is this waveform AC or not? Or is it DC or not? So this is a DC machine, right? The voltage is AC. So we're not talking about this one a little bit more. All the DC machines, they are really AC machines. But if you rectify this one, right? If you rectify this one, it becomes DC, right? Yeah. We'll talk about commutator. So this is one simple question sometimes I ask, or if I'm going to interview somebody to see how much they know about the basic of machine. I'll ask them, okay, if I have a DC machine, those on the power system, they should know this one very simple. Where's my core loss? I mean, where's my core loss? Do you have it in the stator, in the rotor, both of them, none of them? Where's my core loss? Can you tell me core loss relates to what first? Forget my question. Core loss is because let me see, can you remember anything? Because if you don't relate to what you do,
It's the magnetic field core. Eddy current?
Yeah, the magnet.
Magnetic field is part of that, but no, I'm not looking for magnetic field. Is a hysteresis loss and the eddy current loss, but it's related to what?
Material.
Frequency. Remember? We said hysteresis loss is KH Dm f to the power what was that? KH times Dm to the power of n, and for the eddy current was Ke Fs squared Bm squared, right? So now, kind of remind you what was the core loss, and if you read your chapter 1 of your book, I didn't teach that part. I didn't teach that part because we went through it in the transformer. There is one section about core loss and hysteresis and those. You can read it if you are not familiar with that. Now tell me where is the core loss here? Core loss means the losses we have in the in the middle part of the machine. Where's the core loss? No, I'm not saying depends to what, I'm saying where do we have a core loss?
In the rotor?
And that's polarity.
In the rotor? Who is saying in the rotor? Why?
I would say because as it spins, the voltage is being generated in the conductors that are moving. So the speed is going to depend on how much we lose.
No.
No?
No, we're talking about loss, where we have loss. Do I have a loss here? Let me say this.
No.
No. Who said no? Don't worry, who said it was correct?
I'm assuming that the permeability is really high of that material.
No, we're not because of that. There is no loss, but not because of that. What is this current? It's a DC current, right? So this circuit, what is the frequency? See, this one is part of this circuit, right? What's the frequency there? 0, right? Wherever we have a DC system, there is no core loss, right? Because the frequency is 0. Okay? Here there is no loss. But if you look at here, yes, the name of machine is DC machine. But you can see in this conductor, they have an AC voltage or AC current, right? There is a frequency here. So the core loss is related to the rotor of the machine. So if you look at the DC machine, core loss is in the rotor of the machine. When we get to the induction machine, I'm going to ask you the same question. You tell me where is the loss? Where is the loss? You know?
So does increasing the number of poles reduce the loss in that sense?
No. We'll talk about that one. No. It's going to be kind of increasing. I'll tell you why. But no. So.
So then would a single phase motor have less loss than a three-phase motor?
Why?
Like if you said we'd have more.
No, I cannot tell you which one has less or more, but I can tell you does, because it depends on the material, what material you're using. But to say which one has more or less depends on a lot of things, you know. What's the frequency, how much is the DM, what kind of material you have, how big is the machine, all those kind of things. But right, my question is, where is the loss? You know, that's the question. Now, we showed here, this conductor moving this way is going to be like this. Well, let's look at this conductor at the same time. What's the polarity for this one? It's opposite, right? If I look at this one, it's going to be E2, right? If I look at here, how much is the voltage here?
2E.
Huh?
2E.
2E. Right? This conductor and this conductor, this is not plus, this is positive, right? E here, but see minus plus, they're like a series, right? They're going to get 2E.
Can you show how you got the polarity for up and down all the time?
Yeah. I'll show it for the down, but you know you can go for down. So this one comes here, let's put it here. So we say B, right? B should be this way, and the movement is up, right? So you put it this way. I put it for when it was here, you know?
You use your right hand.
So basically it's this way. Sorry.
Professor, I think you're using the wrong hand.
Is based on, oh, you're right, you're right, you're right, sorry. Yeah, you're right. I use the left hand, I should use the right hand. You're right. So thank you for that. So look at here, B, and the polarity is like this. This is inside the board. This is positive, this is negative. I'm not going to explain this, but this one is the opposite of that one. So this one is like, because one of them is going this way, right? Is going up. The other one is coming down, right? The direction is opposite. Now, let's talk about this. How much was, see, I talked about this conductor. This is the induced voltage, right? So this is the current or voltage. I have this conductor, right? When we talk the current and voltage, we are talking about the electrical, you know, parameters, right? If I'm going to look at this one electric-wise, how much is this one? Let's call this one theta E. How much is this one? 180 degree, right? And this from here to here is 300. So basically this is a 90 degree. This is the electrical axis. Electrical axis. 0, 180, 270, and 360, right? And it is, right?